Yay!
All right, let's do a simple example of a grand principle in physics, and that is conservation of momentum. This one is going to be pretty simple. This is called 1D. In other words, one dimension. So I'm just going to talk about two carts along some sort of a rail or something, so they can only go forward and back just in one dimension. So what I've got is two different carts. One is 2 kilograms, the other is 4. Suppose the 4 kilogram one is at rest, so we'll keep it pretty easy the first time. The 2 kilogram one is moving at 12 meters per second to the right, and then they collide somehow. And then what you notice afterwards is that the first one, the 2 kilogram cart, is moving backwards at 4 meters per second. And we want to figure out what the speed of the 4 kilogram one was, the one that was at rest. And the conservation of momentum is going to let us do it. So here it is. Here's the idea. If something is conserved, remember what that means. It means that it's the same before and after. And by the same, what we mean is the total momentum of the system before is the total momentum of the system after. And these are vectors. All right, so the total vector momentum before equals the total after. And by total, I mean total, like we total it up. We do the momentum for each object, and that equals the total. Okay, so let's see. So in this case, if I write out all the possible terms, it'll look like this. M1 V1 initial plus M2 V2 initial is, well, that's the total initial momentum, right? I just add them together. So this is going to be M1 V1 final plus M2 V2 final. Okay, a whole bunch of letters. In our case, it's going to be a little bit easier because this is 0, right? The second mass is not moving. And I know what V1 final is. Okay, so let's plug in some numbers. Let's see what happens. So let's see, this is going to be 2 times, actually, let me go ahead and I'll put them in parentheses. So I got 2 times 12. I'm going to leave off the units just so it'll make the numbers a little bit clearer. The second term is 0, right? And then I got M1 V1 final. Okay, so I got a 2 V1 final. Oh, so now we have to be careful. These are vectors, right? So it makes a difference if something is going to the right or to the left. So if it's going to the left, I'm going to call that negative because I called going to the right positive. So this is going to be minus 4 plus, oops, I already know what M2 is. So this is going to be 4, and this is what I'm trying to find, V2 final. All right, so this is going to be 24 minus 8 plus 4 V2 final. Okay, well, this is going to be pretty easy. So V, you can verify without much difficulty, V2F is going to be 8, a positive 8 meters per second. Okay. So far, so good. So it really does make a difference right or left. You got to remember those negative signs. That's where people normally make mistakes. And it's a pretty simple process. Just the whatever momentum is before is what it is after, and then you can solve for what you need. There's another way to look at this. If the momentum is conserved, that means that whatever total momentum I had before equals after, but that also means that whatever one object lost, the other one gained, right? So look at this one. This one has a plus 24 units of momentum going into the collision. And then after the collision, it's got a minus 8, right? So we can look at it in terms of delta P. So delta P1, what happened to the object 1? It lost 32 units of momentum, right? So this is minus 32. What are the units of momentum? Kilogram meters per second, right? So whatever one of them lost, the other one had to gain. So initially, the other one has 0. And finally, what we said was this thing is going at 4 times 8 plus 32. So sure enough, the first one lost 32, and the second one gained 32 kilogram meters per second. So it's another way to look at it. Both really, if you think about it, say the exact same thing. But it's almost sort of like a monetary transaction, right? Money might change hands, but the total amount of money in the system better stay the same. It's just that it might have changed hands between you and someone else. All right. What about, let's talk about one more case that's pretty easy. What about the case where these two objects stick together, right? If they stick together, let's draw that. Let's draw the final case. If they stick together, there's that box. Somehow they stick together. Oops. For some reason, that gets a square wheel. Not sure why. Maybe if I draw it really slowly and carefully, I get round wheels. Okay. And let's see, this was 2 and 4, and what I want to find is their, what I want to find is their V final after the collision. So if they both stick together, what's going to happen is I'm going to have, initially, I have M1 V1 initial plus M2 V2 initial, but we said that was 0, right? And then if they stick together at the end, I'm going to have M1 plus M2 V final. So now all I need to know is one initial speed, and then I can solve for the final speed, because that's the only variable left that I don't know yet. So they kind of hook together, and they act as sort of a compound object. Okay, so I'm going to have my 2 times 12. The next term is 0. And then at the end, I'm going to have a 6, right? That's the combined mass of the thing if they stick together, times V final. So V final, in this case, is a plus 4 meters per second if they stick together. Okay, and by the way, this is called this thing where they stick together afterwards, just some vocabulary, happens to be called completely inelastic. I haven't talked about elastic and inelastic collisions, but I'm just telling you in advance, this one is called completely inelastic. Elastic, you kind of think in everyday terms about something being bouncy, right? And this is totally not bouncy if they stick together. Sticky is sort of the opposite of bouncy. So if they stick together, this is called completely inelastic. And then all you do is you just sum the masses together at the end. Okay, pretty simple example, and we'll do some more coming up.